So today we're going to start talking about functions, which is basically what we will study for, well, you will study for like the next however many years you're going to take math. So, I can find my notes there. Calculus is essentially just the study of how functions behave. And so it kind of seems like a very small topic when we start talking about it today, but it turns out that the behavior of functions is like an entire branch of mathematics that you could study for years and years and years. So, and is essentially what calculus is all about. So this seems like kind of small stuff today when we start talking about it, but as you'll see, like we kind of build on this idea throughout the semester. So it's important. Although today we're going to talk about a lot of definitions that might not seem like super duper exciting. So we're going to start with the definition of a relation. So this is 2.2. Come on, lady. How did I just delete that whole page? Okay. So 2.2a, relations and functions. So we'll just start with the definition of a relation. So a relation has three components. The first is a set of inputs. Which we call the domain. So the entire set is called the domain. The second is a set of outputs. Which we call the range. And the third is a correspondence. So I have this set over here, which I'm calling inputs, and this set over here, which I'm calling outputs, and then the last component of a relation is a way to figure out which one goes with which. So if you give me a specific input, the correspondence tells me how to find the output that goes with it. So the last component is a correspondence. Or rule that pairs let's say each input with the corresponding outputs. So we have to know what we're starting with, we have to know what we're ending with, and we have to know how to get from one to the other. There's a ton of different ways we can express relations, but in general, we can kind of just think of them as a set of ordered pairs, right? The first coordinate in each ordered pair is the input, the second is the output, and then the fact that they're in the pair together means that they match up. And there's a lot of different ways we can describe these sets. So we'll start with one just kind of in words, which we'll see a lot of because we want to be able to describe real-world situations. So let's say match each student with the dorm they live in. So often when we describe these in words, we kind of have to go backwards. It tells us kind of what the correspondence or rule is. And from that, we figure out what the inputs and outputs have to be. So in this case, Well, one thing to keep in mind about the domain and range is, so the domain is the set of all the inputs for which this correspondence makes sense. So does everybody on campus live in a dorm? No. So my domain can't be every single student on campus, because I can't apply this rule to every single student on campus. So if I pick a student that lives off campus and say, okay, that person's my input, there would be no output that corresponds to them because there's no dorm that they live in. And so for this particular situation, my domain has to be students that live on campus. And I'm kind of glossing over the fact that there's a few places you can live on campus that aren't dorms, but let's just pretend that all the on-campus housing we're calling dorms. And then the output, or the range, the set of outputs, is all dorms on campus. Whoops. And then our correspondence, our rule, it's easier to write rule, is sort of described right here, right? So we kind of started with that. If you give me a student as the input, then the output is going to be whatever dorm they live in. So that's sort of kind of the simplest case. We can just say, okay, I have a bunch of people and a bunch of characteristics about those people, and I match each person with the corresponding characteristic. More mathematically speaking, we can get some numbers involved. So we'll say a group of students was asked how many credits and classes each of them were taking. And here are the results of that poll. Let's see, I think I had a picture. I'll just draw it. So we're just going to use a table. Sorry, I didn't give myself nearly enough room for that problem. There we go. So we're going to make a table that just gives a list of number of classes, and number of credits. Sorry, I know I can't draw straight lines in my life, even when I have technology to draw straight lines for me. So we're wobbly. This one is going to be 2, 1, 4, 3, 2, 3, and then 8, 4, 12, 9, 6, 12. I'll give you guys a second to get all that written down. Okay, so we're going to say the number of classes is our input and the number of credits is our output. So we'll say this is our input. This is our output. Sometimes it's fairly obvious what the input and output are, and sometimes it just has to be told, right? Like here, there's nothing all that interesting about one being the input and one being the output. In particular, we're just making a decision. So there's a couple different ways I can express this set of information. So what this really is just a set of ordered pairs. So we can write it as a set of ordered pairs. So sets always go in curly brackets. 2 is paired with 8. 1 is paired with 4. 4 is paired with 12. 3 is paired with 9. 2 is paired with 6. You're out of room. 3 is paired with 12. Oh, you can't see the edge, okay. That's really just another way of giving a table. So sometimes you'll see it as a list of points. Sometimes you'll see it as a table. These mean exactly the same thing. Another way we can show correspondences or relations is using what we call arrow diagrams, which starts with 2 circles, ovals, potato-looking fellows. And we say, here's my number. So this is called an arrow diagram. This is going to be my number of classes. This is going to be my number of credits. And so in my number of classes, I'm going to list 1, 2, 3, and 4. Notice that even if an input is used in more than one pair, that I'm just listing it once here. So the fact that it shows up in more than one pair will be accounted for by our arrows. But the number 1 exists, is just a single value, right? Like there's not 2 number 1s, there's just one number 1. Same with 2, 3, and 4. The fact that they're used more than once doesn't mean I have to list them more than once in my domain. So everything in the left circle is my domain, and then everything in this right circle is going to be my range. So 4, 8, or 4, 6, 8, 9, and 12. The fact that I put those in order, like numerically, is just because I'm a little bit neurotic. They don't have to be in any specific order inside those ovals. You just have to list them all. And so then we're going to use arrows to show the correspondence. So we have, remember, we have the 3 components of a relation. We've got our inputs, we have our outputs, and then we have the correspondence between each input and output. So in an arrow diagram, the circle on the left gives us our inputs, the circle on the right gives us our outputs, and then we use arrows to show that correspondence. So we have 2 classes corresponding to 8 credits. We have 1 class corresponding to 4 credits. We have 4 classes corresponding to 12 credits. 3 classes corresponding to 9 credits. 2 classes corresponding to 6 credits. And 3 classes corresponding to 12 credits. And so the fact that there are multiple points with an input of 2 is shown by the fact that there are multiple arrows coming out of the 2. And same with the fact that we have multiple points with an output of 12, we just have multiple arrows going into 12. Looks like more than 6, but that's 6. And then the last way we can express all of this same information is using a graph. So one of the things we'll talk a lot about in this class is the different ways to represent relations and functions, which is why I'm showing you the same information in a bunch of different ways. We will talk a lot about how the symbolic representation of a function affects the graphical representation of a function, or how to get one of those from the verbal description of a function. So we have all these different ways of representing things, and they all affect one another. So we need to kind of know how to go back and forth between them. So the last way we're going to do this one, let me get some graph paper here, is with a graph. So I'm going to just, whoa. I'm only going to do the positive x and y axis here, and that's because negative numbers don't make sense in this setting, right? You can't take a negative number of classes, and you can't take a negative number of credits, so it wouldn't make sense for us to have negative numbers on this graph at all. And so that's the only reason I haven't drawn like all 4 quadrants here, because we just don't need them. So the horizontal axis always represents your input. So this is always my input. The vertical axis is always your output. And that is true regardless of what variables are used. So we will often see different variables other than x and y in our symbolic representation, so in our equations. But regardless of what variables are used, your input is always on the horizontal axis and your output is always on the vertical axis. So in this case, this is going to be our number of classes. And I'm going to count by ones here. 1, 2, 3, 4, 5. I went much higher than I needed to. But then on the vertical axis, I have my number of credits. And I'm going to count by 2s, 2, 4, 6, 8, 10. Just because that's what I have room for. And so we're just going to make points corresponding to our ordered pairs. So we have 2, 8, 1, 4, 4, 12, 3, 9, 2, 6, 2, 4, 6, and 3, 12. And that is the entire relation. So one thing to keep in mind is that if we have what's called a discrete set of ordered pairs, which just means there's a finite number of them, right? You can count how many there are. In this case, there's 1, 2, 3, 4, 5, 6 pairs. We can't create more than we have. So if I were to connect these 2 dots, I would be saying that every point on that line corresponds to a pair in my relation. So for instance, there's some person that is taking 1.5 classes for 5 credits. And we know that's not possible, right? You can't take 1.5 classes. So it doesn't make sense to have points between the x value 1 and the x value of 2. And so I can't draw a line between those points, because every time you draw a line, you're giving an infinite number of points that are stuck infinitely close together, and you're saying that every single one of those points corresponds to a pair in your relation. And so in this case, we can't connect any of these dots because it doesn't make sense to have any points in between them. So a couple more definitions. Just to bring all this language together. Where did I put it? So we call the input the independent variable. This is always going to be on the horizontal axis. And typically it is an x value. Like I said, we will frequently see variables other than x and y, but they remain the most common ones used as far as relations, that x represents your input and y represents your output. So unless the definition of your relation tells you something else, if there's an x in there, you can assume it's your input and you can assume the y is your output. Unless, like I said, the description says something else. So then our output, we call the dependent variable. Which, like I said, that's going to be your vertical axis. And it is typically represented with a y value unless otherwise stated. So this idea of independent and dependent, it's not always super duper clear which one is dependent on the other. And sometimes it could be either one, just depending on how it's defined. But the general idea is that, and time is like the best example of this. Let's say that we had a relation that's relating the year to the population of the USA during that year. Well, time passes regardless of what we're talking about, right? We could be talking about population, GDP, whatever. Time is going to pass no matter what. And so time would be independent of anything else that's going on. So time happens regardless of what we talk about with reference to time. Whereas the population, if I want to know what the population is, I have to first know what time it's occurring in, right? So we say that the population is dependent on the time because we can pick any time we want, and that's going to determine what the population was at that time. So in general, if time is involved, it's always your independent variable because you can't stop it, you can't change it, like it is what it is, and it happens regardless of what situation we're in. Whereas we can always, if we know the time, we can say all sorts of things about what's going on at that time, right? And so we say that, in this case, population depends on time. And so population would be our dependent variable, and time would be our independent variable. Like I said, like there are times when you can swap them and it doesn't really make much of a difference. So we usually just define which one we want to be our independent and our dependent variable. So from here, we want to start talking about no, let's do this first. So you don't have to draw this entire graph. We will be doing a lot more reading graphs in the future, but we again just want to relate this back to finding information. So here we gave information about the situation and we were able to get a graph from that. We also want to be able to start with a graph and then pull information about the situation from it. So can somebody give me, here, let me give you a bigger picture. Just a single point on this graph.
6 and 15.
6, 15, perfect. So we are told the average annual precipitation of Medford, Oregon, which is 21 inches a year, which isn't on our graph anywhere because that's just an average. And then the graph shows us the total annual precipitation each year over the 10-year period from 1996 to 2005. So that's what each of those points is, corresponds to one of those 10 years. One thing that we'll see quite often is this idea of like not starting at the year 0, right? Like imagine having a graph that started at the year 0 and then we didn't start measuring precipitation until like the year 1996. We'd have this big, humongous gap, right? And then this like little tiny bit of information. And so for practical purposes, we often just start measuring our input at a value that makes sense to start measuring at, right? Like when we actually started measuring the precipitation. And so an X value of 0 is going to correspond to the year 1995. And then so it's similar to what we did on Friday, where like we said that X was like the number of years over 40, right? So that we didn't have to like have all those X values that didn't even apply to the situation. So if I look at the point 615, what does that tell me in terms of rain and time? So what's the 6 tell me?
It's 2001 years.
Right, so it's been 6 years since 1995. So in 2001, what can I say about the rain in that year? Yep, so the total, I shouldn't say rain because snow counts too, but the total precipitation was 15 inches. And notice this is the total for the year, and that's why the points aren't connected, right? We're not talking about like how much precipitation there was in March or April or May. There can only be one total precipitation for the entire year each year. What about 2002? What was the total precipitation in 2002? So what X value am I looking for?
It's 18.
Right, the total precipitation is 18. We're looking for an X value of what? 7, right? Because in 2002, it's been 7 years since 1995, and so our total precipitation is 18 inches. When was there a total precipitation of 29 inches? So should I find 29 on the x-axis or the y-axis?
1999.
Right. So we're going to find it on the y-axis. I think you're looking at the right place. But it's kind of hard to follow a graph if it's not like you can't draw on it. So this is an x value of 3, which would be what year? 98, yeah. So 1998. And the last thing we want to know is when the total precipitation was higher than average. So what am I looking for if I want to know when it's higher than average?
Anything over 21 inches?
Yeah, I want to find points with an output, so a y value that's larger than 21. So you can kind of just like think of drawing a line at 21. Pretend that's a line. And you're literally looking for all the points above that. So there's 3 of them. There's one at x equals 1, there's one at x equals 3, and there's one at x equals 10. So x equals 1, 3, and 10. But we want to know which years those were. So that's 1996, 1998, and then 2005. That make sense? How we got all those? Any questions? Okay, so we've talked the basics of relations. Now we're going to narrow it down a bit to the type of relation that we actually really care about in math, for the most part. In general, we like things, in mathematics, we like things that we call well-defined. And well-defined just means that basically that if I ask any of you a question, you're all going to give the same exact answer. So we've defined something specifically enough that there is no ambiguity about what the answer is. And so we have a problem here because if I asked you how many credits you're taking if you're taking 2 classes, well, that's not super well defined because there's multiple answers, right? And so you could say 8, you could say 6. If I asked you guys, you'd probably say 8 and 6. But as far as getting a single answer out of this, out of a single question, This isn't super well defined because there's two possible outputs that go with an input of 2. And so we are going to narrow down this idea of a relation to what we call a function. So a function is a relation for which each input corresponds to exactly one output. So you can kind of think of it, a lot of people think of functions as like machines, right? You put something in, it spits something out. If you put something in and there's two possible things it could spit out, it's going to get really confused. So like a calculator, right? Like your calculator gives you a single answer if you put an operation into it. And things would not go so well if you put 2 times 3 in your calculator and there were multiple things it could give you, right? So let's look at a couple arrow diagrams just so we can see the different possibilities here. So these are all relations. Glitchy, there it goes. One of my teachers said the other day that her sets look like potatoes, and now every single time I draw one, that's all I can think about is potatoes. So we'll start with this one. So we'll have A, B, C, 1, 2, 3, and we'll define this relation by saying that A goes to 1, B goes to 2, and C goes to 3. Is this a function? So where does 1 go? Where does 2 go? Where does 3 go? I mean C goes to 3. So each individual input goes to exactly one output, right? There's only one arrow coming out of each individual input. So this is a function. A go there, we'll have B go there, we'll have C go there. So this is where things get tricky. Is that a function? I see some yeses and some no's. Let's do the same thing we did with the last one. Where does A go? Where does B go? Where does C go? So each individual input, does it go to more than one output? It doesn't, right? So the fact that 2 of them happen to go to the same place doesn't make it not a function. Because when we talk about relations, we're thinking of taking individual inputs one at a time. So if we were actually evaluating this function, you can't plug multiple calculations into your calculator at the same time, right? You can only plug one thing in at a time. So if I ask you where A goes, it's like these don't even exist. If I ask you where B goes, it's like these don't even exist. So as long as each one of those individual inputs on the left is only going to one place on the right, it doesn't matter if they're all going to the same place. So one way you can think about it is like if we all went to the airport, we could all get on the same plane and go to the same destination, but it's impossible for one of us to get on 2 planes and go to 2 different destinations, right? So that's basically what a function is it's saying that everybody can go to the same place, but one person can't go to multiple places. So this is a function. And then the last one, it's probably obvious by now that it's not going to be, but we'll draw it anyway. So this one, if I ask you individually, if I say, where's A go? Well, A goes to 1. But if we ask, where does B go? It goes to 2 and 3, right? So that's one person trying to get on 2 different planes at the same time. It's not possible. So it's possible to draw 2 arrows out of it, but it makes it not a function anymore because we have one single input that is trying to go to multiple outputs. So this one is not a function. So let's go back to our examples that we've talked about so far and see which ones are functions. So when we matched each student with the dorm they live in, is that relation a function? So if I give you a single person, how many dorms can they live in? 1, right? So is it a function? It is, right? Because each input, so each student, corresponds to only one dorm. It's okay that a whole bunch of people might live in the same dorm. But if I pick one name out of a hat, there's only one dorm that can go with that name. And so this is a function. Where do I want to write that function? What about this next one? So the classes and credits, is that a function? That one's not, right? Because if I ask you, so if I pick one number up top or one number here on the left, and I say how many credits correspond to that number of classes, well, if I pick 2, it's either 6 or 8, right? So there's 2 possible outputs that correspond to that single input. And one thing to notice on the graph is that these x values that correspond to 2 different outputs, in this case 2 and 3, notice that there are multiple points on that those vertical lines. So this is what we call the vertical line test. We'll talk a bit more about it tomorrow, but in general, if you have any vertical line that goes through more than one point on your graph, that makes it not a function because it means you have 2 points with the same x value and different y values. So that's like having this x value go to these 2 different y values. And that results in 2 points that are right on top of each other vertically. So this one is not a function. What about this one? Is this a function? So there's a few ways we can think about it. One is just by looking at the graph, right? Like if we look at any vertical line on that graph, it only passes through a single point, right? There's not any vertical lines that have more than one point. And then in terms of this situation, it makes sense too, right? Because you can't have 2 different total amounts of rain in a single year. Like if you add up all the rain in one year, that's all the rain there was in that year. It's impossible to have both 15 inches and 17 inches of total precipitation in a single year. So in terms of the situation, it makes sense that it should be a function. And then our graph reflects that because we have on every single vertical line, there's no more than 1 point. So this is a function. Okay, I'm going to give you guys a couple to try while I pass back some papers. Let's do, just going to give you a set of ordered pairs. That's a 0. Okay, see if you can figure out if both of those are functions, and we'll talk about it here in a second after I hand back some papers. Is that a function?
Yes.
It is, right? And when you're given a set of ordered pairs, how can you tell? It's the quickest way, you think.
If the x is all different numbers?
Yeah, so as long as no x values are repeated. So here all our points have different x values. And so that means that every input corresponds to only one point on the graph. What about this graph? Is that a function? In this case it is, and the reason is because this point is open, which means it doesn't actually correspond to a point on the graph. We get infinitely close to that point, and then we jump down to the one that's closed. So if this had been, so this is a function, and this is also a function. But if I had closed this point, if I'd filled it in, then it would not be a function because both those 2 points would exist. And we're going to look a lot more at graphs of functions tomorrow. And like I said, we will be talking about functions for the rest of the semester. So if you don't feel like this makes complete and total sense right now, that's totally normal.